Welcome to today's session, which is going to be on DC power supply. In this session, we talk briefly about a basic disadvantage of the DC converter, why we need a DC power supply. We talk briefly about the various classification of the power supply, which we are going to be discussing, and then we are going to take a look at the transformer model. So, the basic disadvantage of the DC power supply, of the DC converter. And what is that? There is an electrical connection between the input and the output. There is always an electrical connection between the input and the output, which means when the input is grounded, the output will be grounded. This lack of electrical isolation between the input and the output is a very big problem when it comes to DC converters. One way to solve this problem is to use the DC power supply. And what do we use to solve this particular problem? We make use of the transformer in the DC power supply to create an isolation between the input and the output. So using the DC power supply provides us with the electrical isolation that we need between the input and the output of the converter. So that's the first thing. The second thing, in addition to giving us isolation, the turns ratio of the transformer ends up providing an extra flexibility or an increase in the flexibility when it comes to the relationship between the input and the output of the DC power supply. The various classification of the DC power supply. So we have the flyback converters. So the flyback converters are basically derived from the back boost DC converter. Then we have the forward converter, and we also have the full bridge and the half bridge converters. These two power supplies are derived, all of them are derived from the back DC converters. They are all derived from the back DC converters. Before we can do any analysis of the DC power supply, we need to take a very quick review of the transformer models, which we already know. So let's take a very quick overview of that. The first model we have over here is the ideal model. And don't forget, in transformer, we are going to be using the dot convention to indicate the relative polarity of the two windings, to indicate. So the general transformer convention, as current enters into the dotted terminal of a transformer, we expect on the primary side, we expect current to leave the dotted terminal of the transformer on the secondary side for the positive relationship of the voltage and also for the positive relationship of the current. Now, if this relationship change in terms of the way current is entering the dotted terminal and leaving the dotted terminal, then these relationships are going to be maintained, but then a negative is going to be introduced. So we expect that with an ideal model, with a transformer, when current enters the primary side, enters the dotted terminal of the primary side, we expect current to leave the dotted terminal of the secondary side, so that these relationship in terms of the voltage, the turns ratio, and these relationship in terms of the current are going to hold. Let's take a very quick look at the detailed transformer model. So in the detailed transformer models, there are some parameters. The first one here is L1 and L2, which represent the leakage inductance of the windings. Then we have R1 and R2, both on the primary and the secondary, and they represent the resistances of the conductors, and they account for the copper losses. So R1 and R2 account for the copper losses. We also have the magnetizing inductance, which is Lm, and then we also have Rm, which is used to represent the core losses. So this basically represents the detailed model of the transformer. Not all these parameters are going to be used in the analysis of the DC power supply. For the flyback converter, one of the most important parameters we are going to be using when analyzing the flyback converter is going to be the magnetizing inductance. So, as a follow-up to that, we have over here an ideal model with the Lm. And what is the Lm? The Lm here is the magnetizing inductance of the transformer, which we are keeping for the analysis, especially when we are dealing with the flyback converter. One important note, very, very important note. For periodic operation, for both the current and the voltage in the transformer circuit, we expect the magnetic flux in the core to return to its starting value at the end of each switching period. So the magnetic flux in the core must return to its starting value at the end of each switching period. Very, very important. If this does not happen, then what's going to happen? We have it over here. The flux is going to increase in the core, and eventually the core is going to go into saturation. The core will be saturated. As soon as you have a saturated core, as soon as you have your core saturated, then it cannot support a voltage across the transformer. So as soon as we get the core of the transformer saturated, we cannot support a voltage across the transformer winding. The currents which are going to flow in this winding are then going to be so high, and they are going to be beyond the design limits of the circuit, which means that your windings are going to start heating up, and if you don't take care, you are going to destroy and bend the transformer, which is a very, 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 very expensive device. Very, very expensive device. Therefore, the value of Lm, to make sure the magnetic flux in the core returns to its starting value, is a very important design parameter when dealing with the flyback converter. This session is going to be ended here, and the next time we meet, we are going to start talking about the flyback converter. Thank you.